Okay, so what we're going to do is we're going to start by making a square wave. So here's what I'm going to do. I'm going to hit next iteration real quick. All right, so here's what you've got. Here you've got a sine wave, or a cosine, or whatever. A cosine and a sine are the same thing with a little phase shift. Let's not split hairs over that. So here I've got a cosine. Here I've got the same cosine. And what this is telling me is that the amplitude of this cosine is 0.64. And that's its phase shift, right? Minus pi over 2. And don't worry about how I came up with those numbers. That's the magic-y part that we're going to work on starting today. So according to some formula that you don't know yet, I cooked up these numbers, all right? And over here is your plot. Okay, so the first cosine had amplitude of 0.64 and a phase of minus pi over 2. So far, so good? All right, now let's add another cosine. Oh, this cosine, the next frequency looks like it has an amplitude of 0. So there's my cosine with an amplitude of 0, nothing changed. Okay, here's my third signal. Now look what I've done. So I've still got my original cosine. Now here's a new cosine I'm adding. Now let's compare it to the first cosine. Okay, its amplitude is smaller. The first one was 0.64, this one's 0.21. So here's your 0.64. Then we had a 0 amplitude cosine. Now we have a 0.21 amplitude cosine. All right, yes?
How does the 0 affect it?
It didn't. It didn't affect it at all. It just, well, the zeros are the zeros have to do with, I have to check every multiple frequency, and it turns out that some frequencies I don't need any of at all in order to make this work. That's what that's telling me. We'll get more into it. Don't worry about the 0 now. Just, if you can in your mind, just like skip over that part. Yes?
So you're technically saying that some frequencies you would need more.
That's right.
You would change the amplitude, but this one you didn't need any.
I didn't need any of it. Exactly. Right? Some frequencies I needed more of, some I need less of, and some I need none of. Okay? And that's exactly what the recipe is showing me. This frequency I needed that amount of, this frequency I needed that amount of, and this frequency I didn't need any of. So up here I have those individual cosines, and down here I've got their sum, right? If you take the blue signal plus the black signal, you get whatever's down here. Okay? So already that's just two cosines. And if you look at it, it kind of makes sense because I have my original cosine, but then right when the original cosine was going up, I added in this other cosine which kind of goes down a little bit. So the up part and the down part kind of cancel each other, and you get this flattening of the cosine up here. All right.
The second one has a higher frequency than the first one, right?
That's right. The black one has a higher frequency, doesn't it? Do we all know what a higher frequency signal looks like? It oscillates more frequently. Right, exactly. In fact, this one, if you look at the black one and the blue one, the black one has 3 times as big a frequency. Because let's say you start right here where my cursor is. Okay, let's count periods of the black signal. 1, 2, 3. In 3 cycles of the black signal, how many times did the blue signal cycle? Once. So the black signal is 3 times the frequency. Okay, so here's 1 times the frequency, 2 times the frequency, 3 times the frequency. Okay, so let's keep going. Turns out I'm not going to need any of the even frequencies. So I know that one yielded nothing. Now I get another one. And another one. And another one. Okay, wash, rinse, repeat. So what's happening to the sum of those cosines? What's it turning into? Yeah! Okay. Now, is it a perfect square wave? No, of course not. Why? Because I stopped. What do I need to do if I need to get all the way to a perfect square wave? Infinity, right. So good luck with that. But mathematically it works, right? If you were to, so essentially what I'm doing is I'm just adding together a bunch of cosines in just the right amounts, and I'm showing that I can build a square wave out of them. What we want to do is basically think about this the opposite way. I want you to look at a square wave signal, and I don't want you to think square wave. I want you to think, oh, that square wave contains some low frequencies and some high frequencies. Okay, in roughly those proportions. Okay, maybe a square wave is special. Let's try a different kind of wave. Should we try a sawtooth? So exactly the same process. Okay, these are the cosines I'm going to be adding together, the individual cosines, and down here you're going to see their sum. And over here on the right-hand side, you're going to see how much I need of each frequency, magnitude, and phase. All right, so there's 2 cosines. 3, 4. So you can see the amplitudes are different than before, right? The amplitudes and phases are different. If I just restart that real quick. Before, I had 0.64 and minus pi over 2 is my first one. Now I got 0.16, okay? In the previous one with the square wave, this harmonic had 0, right? Now it's not 0, now it's 0.08. That's totally different, okay? And this phase shift is positive pi over 2. That's different. So what's changing is not the frequencies, it's how much I need of each frequency and the phase shift. All right, so we add, and we add, and we add, and we add. And if I do enough of them, part of what you're seeing is the limitations of the resolution on the projector, I think. But can you imagine that if I kept going, I would get a perfect sawtooth wave? Really cool, right? I'm going to build a sawtooth wave with all those sharp edges that it has out of soft, cushy cosines. Pretty neat. All right. Then you can get really crazy, right? That's one I call bizarre. There's bizarre 1 and bizarre 2. It's a square wave and a sawtooth. What happened? Oh, I got the beach ball of death. Come on, MATLAB. Chugga, 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 chugga. Oh, there we go. What's my computer doing? I don't even have the internet open for it to get busy with. All I'm doing is adding cosines. Isn't that nuts? So look, even this weird shape, which is like half sawtooth, half square wave, I can build it out of cosines, provided I know how much I need of each frequency, right? How big to make each cosine and how much to shift it relative to all the other ones. If I can get that squared away, I can build anything. Isn't that wacky? Okay, there you go. So that was my claim, is that if you know how to build cosines, you can build anything. And so the reason we're doing this is that I want you to look at this signal and I want you to think about what frequencies does it contain. Because that's going to be a very useful thing for engineers to know. When you look at signals, it's often a lot more useful to think about them in terms of a signal contains some low frequency content and some high frequency content and some mid-band content or whatever, like blah, blah, blah. So the point is that when you look at a signal, if you can understand how to break it into cosines, then you can answer the question of how much does it have at each one of those frequencies. All right, look at this one. It's got low frequencies and then high frequencies, and it looks like it goes up and down and up and down. Right? You need different amounts. So that's kind of where we're heading. So I hope this example will prove to you that my claim that if you can build a signal out of cosines, then if our goal is to say what's the frequency content of this signal, then all you need to do is to figure out how much you need of each cosine, and you've answered the question. Now we just need to know how to do that. Yes. You have a question?
Well, so you can only build periodic equations.
Turns out you can build anything. Right now I'm just showing you periodic because it's a little easier for the demonstration. And we're going to spend probably like the first 2 or 3 weeks just talking about periodic signals. But as it turns out, you can build anything. And I'll tell you why. It's actually like, again, this is something we'll talk about in more detail when the time is right. But it's actually pretty straightforward. So to answer your question, like, can you do this for non-periodic signals? And the answer is yes, because, like, let's say I want to find the frequency content of a single square pulse that's not periodic. All right. So essentially, what the trick that we'll play one day when the time is there is we'll start by saying, okay, well, I don't know what to do about a single pulse, but I know how to build a periodic signal out of a square wave, out of cosines, right? And then you say, okay, the only thing that now I need to change is so that's my period t. All right. So what if I start making my period bigger? Okay, it's still periodic, right? It just has a different period. Okay, now what if I make my period infinity? It's still periodic, just has a period of infinity, right? Well, if you do that, if you take this periodic signal and make it have an infinite period, what do you think it's going to look like? Ta-da! Right? The math works out. Calculus doesn't care if you make stuff infinity, right? So and that's it. It still works. It's a little different, but it works. So if you can build a periodic signal, you can build an aperiodic signal out of cosines. It's crazy, but I promise you, give me like 3 weeks, and this will all make sense. It totally works.
Why is it so that you can only use cosines to rebuild?
That's a great question. You don't need cosines. It's just that we are going to look at cosines. Okay, so, and that's actually a great segue into the first point that I wanted to make today. Okay, so thank you. So, okay, in the book, which actually I'm going to pull up so that I can make sure that I'm talking, I am, where am I? There we go. Let me pull up today's lecture just so I can make sure I use the right equations and the right examples to match what's in the book. Where are we here? Wow, I am long-winded. Okay, so the question was, why do we have to build everything out of cosines? What's so special about cosines anyway? And the answer is there's nothing special about cosines. I mean, they're special, but they're not unique. So let me start with this. If you build a vector x, right? Or I don't know, you put little hats on it, whatever, x. So let's say x is a vector. So you should have learned in whatever math class you study vectors that the way you represent vector x, all right, is you start with the unit vector in this direction. Remember what we call that unit vector? I. Right, we call it I hat. You ever see that? Okay. And we have a unit vector in this direction. Call that j hat. Okay. And then what we do is we come along and we say something like, okay, vector x is equal to some multiple of some multiple of I hat and some multiple of j hat. Okay? So this sounds kind of like a weird example, but I want you to stick with me. So essentially, I and j are your building blocks. Or rather, you can think of it like those are your ingredients. I'm pretty sure that's not spelled right. That's not an A? No, okay, good. I'm good. All right. Not English major. Well, you got to be able to read and write. Never underestimate the value of being able to speak clearly, write clearly. What's that? Tech writing? Is that what you guys are all?
No, we're English major without the lish and the thing. Oh my God.
Okay, so I and j are your ingredients, and then the 4 and the 3, that tells you how much you need of each ingredient, right? So here's what we're doing. We're taking some signal, let's say our friend the sawtooth, okay? We're taking our signal, x of t, and we're saying, okay, can I represent this signal as in a recipe the same way that I did over here? Can I say that signal x of t contains some quantity of e to the j omega t and some quantity of e to the minus j omega t? Right? So in the same way, those are my building blocks. Right? And why just this one frequency omega? Right? Maybe I need other frequencies as well. Right? So let me call that omega sub 1. Right? For the first frequency that I'm going to look at. But maybe there's some other frequencies as well. Right? Maybe I also need to look at e to the j omega 2t. Okay? And its complex conjugate. Okay, so in exactly the same way that you can build a vector as a weighted sum of building blocks, you can build a signal out of a weighted sum of building blocks. So these are your blocks, right, the complex exponentials. We could use cosines as well. I mean, a cosine is a signal that you could weight. It just turns out that if we think about our cosines in terms of complex exponentials, we make the math a little easier. That's all. Because exponentials are easier to integrate than cosines. In a minute, we're going to start integrating exponentials. And you'll see when I put up the equation, if we had stuck to our original plan of just using cosines, it's awfully ugly to integrate. We'll be doing parts for the rest of, integrating by parts for the rest of our lives. Okay? If you do it this way, it's a lot cleaner and it gets you the same answer. So your question was, why cosines? And the answer is, you don't have to use cosines. There's all sorts of other applications where you can take x of t and rebuild it as a sum of other building blocks. Right? There's this whole kind of analysis called wavelet analysis, right? Where you take x of t and instead of rebuilding it out of cosines, you rebuild it out of wavelets. Right? So a wavelet, there's all these different kinds of wavelets. I mean, a wavelet might be a signal that looks like this. All right? So you might have this wavelet, and then you might have a wavelet that's, let's say, half as thick, which is therefore twice the frequency. Okay? And another wavelet that's a quarter as thick, and so on and so forth. So then you can come along and ask the question of, can I rebuild my signal out of a sum of wavelets? And the answer is yeah. And that tells you something totally different than if you try to rebuild it out of cosines, but you can do it. So you can build it out of wavelets. You can build it out of, there's a transform where instead of building it out of cosines, you build it out of square waves. Okay? I've got a square wave of this pulse width, and a square wave of half the pulse width, and a square wave of half the pulse of that. Can I rebuild my signal out of that? And the answer is yes. Okay? So depending what you're trying to learn, you can rebuild your signal out of different components. Yes?
So the idea is pretty much that the building blocks should be not the same, or they should not be, they should have no similarities.
That's a great question.
Nor should they have, be completely different. They should be kind of, they should be different.
Yes. Okay, so let me answer that real quick, and then I'll. Is your question related, or?
My question is kind of like what came first, the chicken or the egg? Like, okay, if you start with a square pulse of wavelet, how did you get those? Did they come out of cosine?
Well, yeah, they're.
Oh no! I mean, basically, when people do signal processing, like you have to ask a more fundamental question. Like, why bother breaking it into cosines? Because you want to understand the frequency content of a signal. So, since a cosine is by definition a pure frequency, it makes sense to deconstruct your signal into a sum of pure frequencies, cosines. So in that case, it matches the goal that you're trying to solve. Now, in the case of a wavelet, you're trying to do something different. Like you might be trying to look for, like people do wavelets a lot when they're doing spike detection or signal detection. So you might have some noisy signal which may contain a spike buried in it. So what you do is you basically take your signal and you try to rebuild it out of different size pulses. And what you might find is that, hey, like there really was a strong presence in the signal of a pulse with this width, okay? And because there happened to be a pulse of this width buried in the noise. So because that pulse would have had a large coefficient, you say, oh, I bet there's some measure of that pulse buried in this noise signal. So it's like you can rebuild your signal out of anything you want, but it just kind of depends what you're trying to accomplish. Like if you're trying to look at pure frequency, you break it into cosines. If you're trying to look for pulses of this shape, then you use wavelets, pulses that look like that. It just really depends on what the application is. Now, back to your question, which is fundamental. You can use any building blocks you want, subject to the constraints that the building blocks, BB, the building blocks have to basically have three qualities. One is they have to be perpendicular. Okay. So are I and J perpendicular? Yeah. So a fancy way of saying that is if you do the dot product of I and J, if you project one onto the other, you get 0. Right? So there's no J in I and there's no I in J. It turns out the same thing works with complex exponentials. there's no e to the negative j omega t in e to the positive j omega t. And I can demonstrate that, but essentially it's that's the first quality, is they've got to be perpendicular. What's the fancy pants word for perpendicular? There we go. Okay. The second feature is that they have to be they have to be unit magnitude. Right? So this can't have a length of 4 units. I mean, you can. It just gets butt ugly, right? So they basically have to have a magnitude of 1. So I has a magnitude of 1. J has a magnitude of 1. What's the magnitude of this complex exponential? 1, right? It's 1. 1 e to the j omega t. 1. So that works. And then the last feature is that you have to be able to span what we call span the space. So in other words, you can make every single 2D vector as a weighted sum of I and j. Okay? Therefore, I and j are appropriate to use as building blocks. Likewise, over here, you can create every signal out of complex exponentials, provided you use enough frequencies. Therefore, it works. Okay, so those are kind of like your 3 criteria. So as long as your building blocks satisfy those 3 criteria, what you say is that you have a orthonormal basis function. All right, that's a fancy word that you don't need to know, but it's nice to say to impress people, right? Ortho means they're perpendicular to each other. Normal means unit magnitude, right? Normal, things that are normal have a magnitude of 1. And basis simply means you can build every signal or every vector out of those building blocks, right? A basis is like basically just a fancy word for saying building block. So I and j are an orthonormal basis function for all 2D vectors. Likewise, complex exponentials are an orthonormal basis function for all time signals. So whatever, this is like a lot of philosophical math, but I mean, you ask the philosophical question, I give you the philosophical answer, right? Like, this just all works. Okay, and it's kind of cool. Like, it's neat to know where this stuff comes from and why it matters. What do you think? Shall we do an example? Yes?
I was going to say, is this kind of like the fundamental theorem of calculus, where you can build any wave using like a finitely small...
You could sort of think of it like that. You could think of it like that. I'll give you another example that everybody knows. Did you guys learn the Laplace Transform? Yeah, of course you did, right? Well, Laplace Transform is basically the same thing. Instead of building signals as a weighted sum of e to the j omega t, you build signals as a weighted sum of e to the st, where s is sigma plus j omega. Okay? It's a different complex function. But conceptually, it's the same. You're taking your signal and you're re-expressing it as a weighted sum of building blocks. And those building blocks are orthonormal, right? They're perpendicular unit magnitude, and you can create any time signal out of a weighted sum of them. Okay? It tells you different stuff than what we're about to do. It just has different applications.
Does this have, could it be also that because we're accustomed to cosine and sines, it makes sense to just build on that to using the other methods?
It's not because you're accustomed with cosines and sines. It's because cosines and sines answer a very simple question. Okay? When we think about frequencies, right, our goal is to understand the frequency content. It'll become a little more evident further in this semester why I'm so hung up on understanding frequency content. But for now, we'll just assume that I want to know what's the frequency content of my signal. Well, if you want to understand frequency content, the basic building block is a cosine, right? Because for each cosine, how many frequencies does it contain? Exactly 1. It is the only signal that has that property. Okay? Cosine is the only signal that is a pure tone. It contains one frequency and no other frequencies. Therefore, if your goal is to understand the frequency content of your signal, the only possible building block is the cosine. Because anything else that you use is a mishmash. Like if I wanted to rebuild my signals out of square waves, I could do that, but a square wave isn't a pure tone. It contains a whole bunch of frequencies. So breaking my signal into a weighted sum of square waves doesn't tell me anything about how much of each frequency is in the signal. It tells me something else that might be useful, but it doesn't tell me anything about the question that I happen to be interested in today. So if I want to understand frequency, I've got to break it into cosines. The end. It's not because we're familiar with it, it's just because that's the only option. And the only other party trick I'm doing is I just decided that instead of working with cosines, I could basically get all the same information by working with a complex exponential. It's just a little easier. Okay, that's all. So let's do an example. So here's the magical equation that's going to drive you bananas, and it's going to look a little bit like the Laplace transform, which you should have seen. I am going to try to motivate it a little bit for you. I've actually not tried this before in a signals lecture, so I'm going to try to allocate maybe 5 minutes to this and see how this goes. So let's say, for example, let's start with a question that we already know the answer to, because that's always good, right? If you already know the answer, then you'll know if you get it right. So let's say we have, suppose x of t equals cosine 3t. Okay. So in this case, this is easy. We know exactly how much I have, right? I can take this cosine. Can somebody tell me how to express this as a sum of complex conjugates?
1/2.
Actually, I'm sorry. Let me stop. I'm going to do the example that was exactly in the book, and I got my 3 in the wrong place. I beg your pardon. Can we do that instead? I apologize. Okay, okay, complex exponential time. 3/2 e to the j. What's my omega in this case? Omega is 1. So it's e to the jt plus 3/2 e to the minus jt. Okay. So what I want some sort of magical, so this case, it's easy. By inspection, I could determine that this is my value of A and this is my value of A conjugate. In this case, it was easy. I could just look at it. But what happens when we talk about square waves? It's not going to be obvious what the answer is, right? So what I want is some sort of magical function where I stick in my signal x of t, and it says that's your value of A. You with me? That's what I want. I want to know what goes in this box. So what we're going to do is I'm going to tell you what goes in this box, and then we'll try it. And in this case, we'll stick in the cosine, and I know that if the integral works, I know that the answer I get out had better be 3/2, right? Because that's obvious. So here's what goes in that box. Your value of A is going to be equal to 1/t times the integral over 1 period of x of t e to the j omega, e to the negative j omega t dt. It looks a little like, yeah, this is the Fourier transform, right? This is basically the Fourier. It does look. Now, let me build a little. This is the bit that I haven't done before that I want to try to explain. Let me build a little intuition why this works. Okay, so suppose I've got a signal, and let's say x of t looks like this. I'll make it symmetric just to make life easy. So 5, whatever, few samples, right? So that's my signal x of t. Now let's say what I want to do is say, how similar is x of t to, I don't know, this signal? A line. So we can actually answer mathematically how similar they are. And what you do is you take each of these samples and you multiply them. So I'm going to take this times this, this times this, this times this, and so on. So I'm going to multiply all the corresponding samples, and then I'm going to add them. So that's essentially what I'm claiming is going to do. So if I do that, so let's say this is my, my building block, y of t. So essentially what I'm arguing we're going to do is we're going to take x of t, multiply by y of t, and then we're going to add together all the samples. And that will give me a measure of, that measures similarity between x and y.
Is that the same term as correlate?
As what?
Is that the same as correlate?
Convolution?
It's a little like convolution.
Right?
Correlation. It's a little like correlation. Now, let me give you an example. Okay, let's just think about this for a second. Suppose I did this. I compared this y signal with this x signal, and I'm going to get some number. Okay? Now, let's say instead I come along and instead of using that y signal, I'm going to try a different y signal. And that y signal is going to look like this. It's going to look basically exactly like the x signal. Now when I do my multiplication and summing, am I going to get a number that's bigger or smaller than the one I just had? It's going to be bigger, right? Because this number is going to be multiplied by, basically like everywhere where this number is big is going to line up, right, and give me a big number, right? I'm going to get everywhere where this number is big, it's going to line up with another big number, and they're going to add together to give me a big number. So when they're similar, everything lines up. All your multipliers are big, and then you wind up with a big sum. So when they look similar, this whole business of multiplying and adding gives you a big number. And when they look dissimilar, this process of multiplying and adding gives you a small number. Yes?
Well, what if the y of t was larger than the actual x of t? Then it will result in a larger number.
Ah, that's a great question. And that's why y of t has to be normalized. Remember how we talked about an orthonormal basis function? Right? So one of the things I would have to do in order for this to not be crazy is I would need to make sure that, let's say, if I took y of t and summed it over all values, or like maybe summed the squares of all those values, it would equal 1. So it had like some sort of unit energy to it. Right, because otherwise I could make y arbitrarily large, and then it would keep getting bigger. Right. So there has to be some sort of normalization process. That's a great question. Okay. I don't want to get too bogged down in this. This is just sort of like, if this helps you to realize the intuition behind what's happening here, then it's useful. Okay? So if you want to see how similar two signals are, you multiply them and you integrate. Or you add across samples. So that's what I'm doing here. I'm trying to answer the question, how similar, or how much e to the j omega t is in x of t, question mark. Okay, so look what I'm going to do. Just like I was sort of doing with my little hand-waving example over there, I take x of t, I multiply it with, it turns out this only works if you use the, not e to the j omega t, you have to put its complex conjugate there. So over here, it's not just x times y, it's x times y conjugate, whatever. Okay. So basically, you multiply x times y against each other, and then you integrate across all samples. Okay. Now, this is a periodic signal, so by definition, I only integrate over one period, and then I'm going to normalize by the period. So holy cow, what a mess.
That is convolution, right?
No. It's close. It smells like convolution. It smells convolution-ish, but convolution's worse. Okay, so we're going to run this integral, and we're going to get 3/2. And I have exactly 6 minutes budgeted for this task, because then you have a quiz. So, first question. What value of omega should I use in this problem? All right. So I'm going to ask how much omega equals 1 is in that cosine. We good? Good. I need a value of t, right? Because my integral requires a t. Well, start with the f. Frequency is 1 over 2 pi. And therefore my period is 2 pi. Okay. Let's write the integral. Equals 1 over 2 pi times the integral over 1 period. Now, I can either go from 0 to 2 pi. I can go from minus pi to pi. It doesn't matter. As long as you hit 1 period, it doesn't matter. So what do you want to do?
0 to 2 pi.
Okay, you picked the hard one. That's fine. 0 to 2 pi. My x of t signal is 3 cosine t e to the j, negative j, and now I'm going to substitute in my value of omega, 1, t dt. So we need to solve that integral. How do you want to do it? You have two, you can do this in one of two ways. The painful way and the not painful way. The easy way is to convert your cosine into a complex exponential. Then you're good to go. The hard way is by parts. And you know, whatever, to different strokes for different folks. You get the same answer if you do it right. So let's do this. I'm going to pull out the 3. Is that good? Okay. And I'm going to rewrite my cosine as a complex exponential. So that's going to be 1/2 e to the jt plus 1/2 e to the minus jt. And that's going to be times, so that's my cosine, times e to the minus jt dt. We good? Have I lied to you yet? Sweet. Okay, I can pull out that 1/2. So it's 3 over 4 pi integral. Now, e to the jt times e to the minus jt. It's e to the 0, which is 1. Have a nice day. All right. And then I've got e to the minus jt times e to the minus jt, e to minus 2jt dt. Now we can integrate, right? No integration by parts. Integration by happiness. Right? What's the integral of 1? T. What's the integral of that mess?
1 over negative 2j times.
Yep. So 1 over minus 2j, plus 1 over minus 2j e to the minus 2jt on the limits from 0 to 2 pi. And we've still got our coefficient out front.
I'm sorry, where do you get the minus 2jt from?
Because I did, you mean here?
Yes.
I did e to the minus jt times e to the minus jt. You add the exponents, it's e to the minus 2jt. Okay, let's sub in our limits of integration. Is this going to work? I don't know, let's find out. So if I sub in 2 pi, I get 2 pi minus 1 over 2j. Now it's going to be e to the, I got to sub in 2 pi into this expression. E to the minus j 4 pi. Okay, I like that. So now it's minus, and now I have to sub in the 0. So 0, if I sub in 0 for t, I get 0. And if I sub in 0 for this t, I get 1. So it's minus 1 over 2j. Now I got some simplifying to do.
1 over 2j cancels.
Talk to me about this term. Yes?
That's just going to be 1.
because that's the cosine of 4 pi.
Everyone has to get good at this, right? This is equal to cosine minus 4 pi plus j sine minus 4 pi. What's cosine of 4 pi? Minus 4 pi, 1, right? That's 1, that's 0. Another way to think about this, here's your real and imaginary axis, right? So, remember we talked about this? So I need to go minus 4 pi radians. So here's minus pi radians, minus 2 pi radians, minus 3 pi radians, minus 4 pi radians. What's that number? 1. Get good at that. So, to simplify, 3 over 4 pi times 2 pi minus 1 over 2j minus 0 plus 1 over 2j. The 2j's cancel. I'm left with a 2 pi. 2 pi and the 4 pi cancel, and I'm left with, wait for it, which is exactly what I knew I was going to get. But that was sort of the point of the example. Now, when we reconvene on Monday, we'll answer the next question. We'll start with the same cosine, and instead of saying how much e to the jt is in my signal, I'll ask you how much e to the j2t is in the signal. We'll try a different frequency. So just out of curiosity, how much of this cosine, cosine of frequency 2, is in this signal? None. Is there a term that says plus something or other cosine 2t? 0. Therefore, if it is true that this function is in fact a good and useful function that always gives us a meaningful answer, then not only should it correctly predict that the answer when you stick in this value is 3 halves, it should also predict when you stick in this function, you get 0. You can try that by yourselves over the weekend. It should work out perfectly, but either way we'll do it on Monday.